Making tunnel-grade concrete demands incredible precision. A single cubic meter can contain nearly 400 kilograms of cement, more than 700 kilograms of sand, over 1,000 kilograms of crushed stone, carefully measured water, and advanced chemical admixtures. These additives slow curing, improve strength, and stop seawater from penetrating the finished structure. What looks like ordinary concrete is actually a carefully engineered recipe. Imagine driving your car beneath an ocean while millions of tons of water press down just a few meters above your head. One tiny mistake during construction could flood an entire tunnel in minutes. Yet engineers around the world build these incredible passages every year with astonishing precision. Today, you're going behind the scenes to discover how underwater tunnels become one of the greatest engineering achievements on Earth. Most people only see the finished tunnel. They never witness the giant machines, the thousands of workers, or the years of planning hidden beneath the waves. Think about this. Before a single tunnel section reaches the seabed, engineers study the ocean floor, map every layer of rock and clay, and prepare for conditions that can change without warning. But here's what nobody tells you. The hardest part hasn't even started yet. Full microphone narration. But steel is only part of the story. The hydraulic system relies on precision machined cylinders, pumps, valves, and hoses manufactured from specialized metals and synthetic materials. Rubber components often begin with natural rubber harvested in Southeast Asia and synthetic compounds produced in advanced chemical plants. Thousands of individual parts must travel across continents before they ever reach the factory floor. Think about this. A finished amphibious excavator may weigh more than 30 tons, yet its flotation system must distribute that weight carefully enough to travel across terrain that would swallow ordinary construction equipment. That requirement forces manufacturers to use huge quantities of precisely engineered steel while controlling every gram of unnecessary mass. It's a balancing act that begins long before the first weld ever appears. Of course, extracting and processing these raw materials comes with a cost. Mining operations consume enormous amounts of energy, while steel production remains one of the world's largest industrial sources of carbon emissions. Manufacturers now invest heavily in recycled steel, cleaner energy sources, and more efficient production methods. Yet even with these improvements, creating the raw materials for a single amphibious excavator remains a remarkable industrial undertaking. The moment the raw materials enter the factory, the pace changes completely. Huge steel plates weighing several tons move across the production floor on overhead cranes. Computer-controlled plasma cutters begin carving precise shapes that will eventually become the excavator's floating pontoons. Temperatures inside the cutting zone can exceed 20,000 degrees Celsius, or more than 36,000 degrees Fahrenheit, while cutting heads move at speeds approaching several meters per minute. The sound is a constant roar of electricity, hot metal, and flying sparks. Next comes bending and forming. Massive hydraulic press brakes apply hundreds of tons of force to shape thick steel plates into the curved structures needed for flotation pontoons. Some sections require multiple forming cycles lasting several minutes each. You can hear the deep groan of machinery as steel slowly changes shape. What looks effortless from a distance actually demands extraordinary precision because even a few millimeters of error can affect buoyancy. 9 Microphone narration. The formed sections now move to welding stations where the real structure begins to emerge. Robotic welding systems and highly skilled welders join hundreds of individual steel components together. Welding arcs reach temperatures near 6,500 degrees Celsius, or almost 11,700 degrees Fahrenheit. The air fills with the smell of heated metal, while blue-white flashes illuminate the factory like lightning storms. A single pontoon can require dozens of hours of continuous welding. The final step is a brutal pull test where winches are subjected to 125% of their maximum capacity under 500 bar of pressure. The entire rig groans under the strain, emitting a low, terrifying hum as cables vibrate. If the components survive this 30-minute torture test without a single microfracture, they are cleared for global deployment. Once welding is complete, technicians inspect every critical seam using ultrasonic and magnetic particle testing. Sound waves travel through the steel, searching for hidden defects invisible to the human eye. Even tiny cracks can trigger repairs before production continues. Most people never see this stage, yet it determines whether the machine survives years in some of the harshest environments on Earth. Meanwhile, another part of the factory builds the excavator's hydraulic heart. CNC machining centers cut steel components with tolerances measured in fractions of a millimeter. Rotating tools spin at thousands of RPM while coolant sprays across glowing metal surfaces. The machines never seem to stop. Day and night, they transform raw metal into precision cylinders, valves, and pump housings that control every movement of the finished excavator. Next comes one of the most critical moments. High-performance concrete flows into giant steel molds through powerful pumps at nearly 120 cubic meters per hour. Powerful vibration systems shake the molds thousands of times every minute, forcing out trapped air and packing the concrete tightly around every reinforcing bar. The entire factory rumbles as the fresh concrete settles into place, creating a structure strong enough to resist decades of underwater pressure. Fresh concrete begins an invisible chemical reaction called hydration. As cement combines with water, it generates heat that can raise the core temperature to nearly 65 degrees Celsius, or 149 degrees Fahrenheit. Engineers place dozens of sensors inside every section to monitor the temperature around the clock. If the concrete cools too quickly, tiny cracks could weaken the entire tunnel before it ever reaches the sea. Fresh concrete begins an invisible chemical reaction called hydration. As cement combines with water, it generates heat that can raise the core temperature to nearly 65 degrees Celsius, or 149 degrees Fahrenheit. Engineers place dozens of sensors inside every section to monitor the temperature around the clock. If the concrete cools too quickly, tiny cracks could weaken the entire tunnel before it ever reaches the sea. After pouring, every tunnel section remains inside the mold for nearly 24 hours before workers carefully remove the forms. The concrete continues curing for several weeks until it reaches its full design strength of more than 50 megapascals. During this time, automated sprinklers keep the surface moist, preventing shrinkage and improving durability. The smell of fresh concrete fills the air while giant cooling fans hum across the factory floor. Then comes the ultimate challenge: stress testing. Hydraulic systems apply forces equal to thousands of tons, simulating decades of traffic, earthquakes, and water pressure. Sensors measure movement to fractions of a millimeter while computers record every tiny change. The deep rumble of hydraulic pumps echoes through the testing facility as engineers watch for even the smallest sign of weakness. Even with advanced automation, experienced workers still perform the final inspection. They run their hands across sealing surfaces, measure critical joints, and spot tiny imperfections that machines sometimes miss. Years of experience allow them to notice details no algorithm has learned yet. It's a powerful reminder that human skill still stands beside the world's most advanced technology. Underwater tunnel construction has grown into a global industry worth tens of billions of dollars every year. Thousands of engineers, divers, welders, surveyors, and heavy equipment operators work together on projects across the world. Countries such as China, Japan, Norway, Denmark, and South Korea lead the industry with some of the largest and most advanced underwater tunnels ever built. Every new project pushes engineering a little further. Did you know that some tunnel sections weigh more than 70,000 tons? That's heavier than many aircraft carriers. Did you know engineers can position these enormous structures with an accuracy of only a few centimeters underwater? And perhaps the most amazing fact of all, many of these tunnels are designed to serve safely over the past 120 years beneath the sea. Tunnel construction has changed dramatically. Engineers now use digital twins, artificial intelligence, autonomous underwater vehicles, and robotic inspection systems that simply didn't exist a generation ago. In the next decade, smarter materials and fully automated construction equipment could make underwater tunnels even safer, faster, and more affordable. The future is already taking shape beneath the waves. From iron ore buried deep inside mountains to giant concrete sections resting silently beneath the ocean, every underwater tunnel tells an incredible story of determination, science, and human imagination. The next time you drive through one, you'll know that every meter represents years of planning, millions of working hours, and engineering performed with astonishing precision. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory. Finally, engineers connect the new section to the previous one using powerful hydraulic jacks that pull the two massive structures together with incredible force. The rubber gasket compresses into a watertight seal, and pumps remove the remaining water trapped between the sections. A connection that takes only a few hours completes months of manufacturing and years of planning. But how do engineers know that every joint will remain perfectly safe for the next 100 years? That's the mystery we'll uncover next. Before a single tunnel opens to traffic, engineers inspect every centimeter with technology that can detect defects invisible to the human eye. Laser scanners create a complete 3D model of each tunnel section with an accuracy of less than 1 millimeter. AI-powered vision systems compare millions of data points in seconds, searching for cracks, surface defects, and tiny dimensional errors. What takes a person days, computers finish in just a few minutes. Quality control goes far beyond looking at the surface. Ultrasonic sensors send high-frequency sound waves through the concrete to detect hidden air pockets and internal cracks. Every steel weld receives detailed inspection, while pressure tests confirm that waterproof joints can resist years of seawater exposure. Less than 2% of tunnel components require repair, and anything outside the strict tolerance limits never reaches the construction site.